All right, so now we're trying to solve this type of differential equation. Y double prime, AY double prime plus BY prime plus CY equal to 0. So let's try to move on to second order differential equation. And once you begin working on second order differential equation, the problem suddenly becomes very hard. I mean, you may have thought that first order differential equation is already so hard to solve. Think about how harder it would be to solve second order differential equation. Right?
This is second?
Yeah, because why is it second order?
Double
prime.
Yeah, you have two derivatives, right? And so because it's so hard, there are two things that we're going to do. One is that we will try to limit ourselves to very specific, limited sets of second order. Okay? Because, I mean, if it gets slightly modified, suddenly it becomes really hard. So here, this is the simplest second order differential equation you can think of, which is called, this one is called, by the way, second order, because it's two derivatives. Constant coefficient because you can see that y double prime, y prime, and y, they all have the coefficient functions as constants. A, B, and C are constants. Okay? This is called constant coefficient. Linear meaning all of these have power of 1. Right? You don't see y squared or y cubed or sine of y. Those are not allowed. Okay? Sine of y prime, y double prime squared, those are not allowed. It's always just the first power. That's what linear means. And also, you don't want any term that has x in there. So, second order constant coefficient linear, homogeneous. And by the way, this unfortunately we're using the same word for this equal to 0, and also in our first order case we were using this word homogeneous to mean something totally different. Over there, homogeneous meant that you can transform the equation as y prime equals the function of y over x. Okay, that was just some special class of differential equations. In the second order case, when we say homogeneous, it just means that the right side is equal to 0, and the left side you have only y's in there. Okay? All the terms must have y or y prime or y double prime attached. You don't have a single function of x without any y attached. That's not allowed. That's what homogeneous means. Okay? Differential equation. Okay, so that's what we want to solve first. Okay, you might complain that this is very complicated, but every description here is a restriction on what type of equation we're trying to solve. So the more restriction you have on the thing that you're trying to deal with, the more specific you know about what you're dealing with, and it makes it easier. Okay, so what's going to happen is later on, after we get comfortable with this one, we will drop the homogeneous condition. It gets slightly harder. Okay? And then later on, after that, we're going to drop the constant coefficient and make the coefficients as functions of x. And that gets even harder. Okay? And then that's also the case where you do nonlinear, okay, second order nonlinear differential equation. And that one we're not even going to bother with in this course, because there are like people who are getting PhDs just by solving some second order nonlinear differential equations. So it's a very tough subject once you get there.
How do you know if like you solved it right if no one people
Oh, I mean, if you have the solution, you can always go back and check, right?
No, I'm talking about the PhD people who are doing it.
Yeah, even if you have the solution, you can. I mean, finding the solution is hard, but if you have the solution in front of you, verifying that it's a solution, that's easy, isn't it?
I mean, you said PhD, so I thought it'd be a little hard.
Well, actually, it's actually much harder than that. Actually, rather than solving it, they actually prove that the solution exists or something like that. Yes?
So homogeneous in this case just means there's no x values, only y's?
No function of x on its own.
And it also means y prime equals xy over xy?
No, that's
No?
that's for a first order differential equation. So in terms of context, homogeneous mean different things, okay? When we were dealing with first order homogeneous differential equation, that word homogeneous over there meant that the differential equation looks like a homogeneous function times y prime equals to another homogeneous function. Here, homogeneous means the right side is 0. I mean, the reason you call homogeneous is because everything here has order 1, order 1, order 1, right? Y of order 1. On the right side, if you had x there, then because it doesn't have any y in it, then y would have, you can think of as some function of x times y to 0th power. Then suddenly your exponent doesn't agree with the left side, which is exponent 1. That's why you call this homogeneous, having 0 on the right side. But I mean, so you can kind of weakly link the word homogeneous with the homogeneous polynomial and homogeneous function like that, but really just don't try to link those two. Here, homogeneous means right side is 0. Okay? All right. So that's the first one. Okay. So one approach in dealing with second order differential equation is that we're going to try to put a lot of limitations so that we can work with some very narrow class of differential equations. Now the second thing that we are going to do is we will not solve differential equations, but we will make guess and check. So the approach will be more like you make guesses and you check if it's the right answer or not. Okay? Yeah. So that's a different perspective. Okay? Instead of solving it completely, you just say, oh, the solution probably looks like this. You plug them in and see if it works. If it's good, then all good. You're done. Okay? Now, why does such approach work? Well, technically, that's not really considered a kosher way to solve things, right? When you're told to solve equations, you really have to do the algebra to find the solution, right? But starting from second order, instead of solving it step by step, this is the approach that mathematicians took. The way they do is, first they show the uniqueness and existence of solutions. So basically, this is the statement that they work with. So, for example, if you had y double prime minus 3y prime plus 2y equal to 0. Suppose you had this differential equation with y of 0 equal to 2 and y prime of 0 equal to negative 1. If you had something like this, then mathematicians already did most of the work. They know that for these types, mathematicians prove that such a differential equation always has a solution. So that's the existence part. And also, when you're giving two initial conditions, then there is a unique solution to this entire requirement. So existence and uniqueness is a very big topic in differential equations. So when engineers try to solve things roughly by numerical methods, they try to either look at the books that mathematicians wrote, or if they can't find it in the books, they would visit a mathematician and show the differential equation. They will ask, does this differential equation have a solution? Is there only one unique solution to this differential equation? Those are the questions that engineers would ask mathematicians, because there are ways to solve approximately, but if you don't know that the solution actually exists or it's unique, then all these numerical methods is meaningless. Okay? For us, existence and uniqueness has the following meaning. It is a way to justify your answer when you made a guess. So it works like this. I made a guess and somehow I found that such and such actually solves this and with everything. Okay? How do I know that I found everything? Well, first, I know that this has a solution, so I'm justified in saying that here I have a solution, right? And not only that, because I know that the solution is unique, if I present you with one solution, then it will be the solution of this equation, because there's only one and I found this one solution. So that's the argument that we are tacitly making. So somehow, starting from second order differential equation, the solutions might look strange because you're not really solving them. You're making educated guesses. I'm going to teach you how to make these educated guesses, and later on, we will the mathematic theorems will justify it without you realizing that it's justified by some mathematical theorem. Okay, so let me give you a taste of how these things will be solved. Okay, and here's the most basic one. Theorem. So if you have a differential equation with constant coefficient and homogeneous, then there's at least one solution that looks like y equals to e to the rx with some value of r. There's at least one solution that looks like this. And this is what I mean by educated guess. I mean, nobody can just look at this and say, hey, the solution is e to the x. I know it's e to the x only because I made it so, but it's hard to do that. But if you know that the solution is e to the rx, then in any case, then all you have to determine is what's the value of r that would satisfy this. And that's how we say it's a solution. So let's see, y prime, what's y prime? E to the rx, and rx has to be pulled out and differentiate. It has to be differentiated because of the chain rule, right? Which is r times the rx, right? So e to the rx, every time you differentiate, r pops out, right? Y double prime, again, when you differentiate, another r will come out and you're going to get r squared e to the rx. And then you plug everything back in there, and you have r squared e to the rx minus 3 times r times e to the rx plus 2 times e to the rx equal to 0. So you see what I did? Y double prime replaced by this, y prime replaced by this, y replaced by this, and this is what I get. I see that e to the rx is a common factor, so I'm going to factor that out. What's left then? If I take e to the rx away, r squared is left. Here, e to the rx taken out leaves you with negative 3r. If I take the e to the rx, 2 is left. And if you look at this, you see that e to the rx cannot be 0 because it's an exponential function. An exponential function can never be 0. So the only way that this could be 0 is when this polynomial is equal to 0. So let's try to solve it. I'm going to take this and solve it here. R squared minus 3r plus 2 equal to 0. R minus 2, R minus 1 equal to 0. So R is 2, R is 1. which means if you plug these r values back into the function, you know that y equals e to the x is one solution. And y equals to e to the 2x. So for r equals to 1, you get e to the x. For r equals to 2, if you replace r by 2, you get e to the 2x. So those are the two solutions. And we're basically making educated guesses. We start with, hey, I know for a fact it looks like something like e to the rx. So let's try it. Does it give us some solutions? Hey, not only we get one solution, we actually get two solutions, which is very good, right? But this is not what we want, because in general, I know that second order differential equations should have two parameters, C1 and C2. So where do they belong? How do we make the most general solution that has C1 and C2? And the way you construct the general solution out of it is by doing the following. If it's homogeneous, then we know that if you have any solution, then any multiple of that solution is again a solution. Because that's the property of being linear and homogeneous. If you have a linear and homogeneous, it doesn't have to be constant coefficient, by the way. If you have a linear and homogeneous differential equation, then you take any solution, any constant multiple of that solution will be another solution. So I know immediately that some constant times e to the x will be a solution. You can check, right? See, differentiating leaves the c, it doesn't touch the c at all. So at the end of the day, you'll still get c times 0, which is just 0. And from here, you can get another c times e to the 2x. And let's try to distinguish these two c's by putting c1 and c2 there. So just taking multiples. And not only that, if you have two solutions, adding them will give you another solution. So if you know that this is a solution and that's another solution, then adding the two will give you another solution. And then once you have figured out that this will be a solution, we're kind of happy, right? We have two free parameters for a second order differential equation. And now all we have to do is make sure that it satisfies these two conditions. So let's do that. So the first condition was that y of 0 should be 2. And that means y of 0, c1 e to the 0 plus c2 e to the 0, which is c1 plus c2, should equal to 2. So we have this one equation to solve. And then y prime of 0 equals to negative 1. That was the second condition. But what's y prime? E to the x differentiates to e to the x, right? So that doesn't change. What do you get if you differentiate this? E to the 2x. 2 comes down, right? So you have twice of c1 e to the x, but then you're plugging in 0 into x, so you put 0 here. So you get c1 plus 2c2, and that has to equal to negative 1. And that leaves you with a system of equations which you can solve. Let's see, c1 plus c2 is 2. c1 plus 2c2 is negative 1. Let's try to solve this. Subtract. I guess that's the quickest way to solve, right? So c1 subtracts to 0. c2 minus twice of c2 is negative c2. And 2 minus negative 1 is 3. So you get c2 equals to negative 3. And plugging that back in here, you get c1 minus 3 equals to 2. c1 minus 3 equals to 2. That gives you c1 equals to 5. And therefore, finally, you can say that the solution is y equal to c1, which is 5 e to the x, minus 3 e to the 2x. And you can, yes?
So, the first one you did, not the y prime, when you get c1 e to the x and c2 e to the 2x,
Uh-huh.
those are two formulas, and then you have a third one, that's them combined. Is that what you said? Yeah, y equals c1 e to
So
the x.
you're asking me, you have one formula, another formula, and three formula. I don't like that approach. This is how you should understand what I'm doing here. If I, without doing any calculation like that, if I suddenly said, hey, there's a differential equation, these are the solutions, how would you verify my statement? If I say e to 2x is a solution to that differential equation, how would you verify my statement?
Plug it back in.
Plug it back in. I will take this and differentiate twice, so it'll be y prime is 2e to the 2x, y double prime is 4e to the 2x. Replace y double prime by 4e to the 2x, y prime by 2e to the 2x, and y by e to the 2x. Compute the left side, and you can see that it actually gives you 0. Okay? So that's how I know that that's a solution. If I claim that this is a solution, how would you do it? Again, just plug in. If you take this and plug it to the left side, you're going to see that it's equal to 0.
So,
You plug this in, you're going to get 0. If you take this entire thing with C1, C2 being arbitrary constant numbers, you can still see that this will satisfy the differential equation. That's how you're going to understand my statement. Yes?
So since e to the x and e to the 2x both equal 0 when you put them in,
Yeah.
it doesn't matter if you add them together because they're still going to equal 0 in the end. And it doesn't matter that
That's
you,
the property of being linear.
Right.
If any of these has squares in it, then suddenly that property is gone.
Right.
You don't have that anymore. Yes. Do you have any other questions?
Yeah, what's the bottom? What'd you do again?
All right. So we have this, right? And this too, you can check that this is a solution by. So how would we verify this? Okay, so to verify, let's see, you have y of 0 so it satisfies the first condition, first initial condition, right? Y prime of 0. Let's see, if you differentiate, that's 5e to the x. If you differentiate e to 2x, that's 6e to 2x, and you're trying to plug in 0 into x, right? So if you plug that in, you get, if x becomes 0, e to the 0 is 1, so you get 5 times 1 minus 6 times 1, so you get negative 1. So you can see that it satisfies the second condition, right?
so this whole thing is just based off of you assuming that y equals e to the rx?
Yeah. Just that's the educated guess. Okay, so
And it worked, right? It worked?
it works most of the time. Sometimes it fails. That's why
Well, it worked for this one, right?
it worked for this one, but sometimes it fails. Yeah.
So what are the other attempts?
It's gonna require many classes to actually get there. Okay. All right. Okay, so this is what you get, and then you can also take the first derivative, which is 5e to the x minus 6e to the 2x, and then second derivative, which is 5e to the x minus 12e to the 2x, and then just replace y double prime minus 3y prime plus 2y by these things that we have. So what's y double prime? It's this one, right? 5 e to the x minus 12 e to the 2x minus 3 times y prime is 5 times e to the x minus 6 e to the 2x, and then plus 2 times the original was 5 e to the x minus 3 e to the 2x, right? And then just multiply and combine the like terms. You'll see that it's true. So 2 times 5 is 10. 3 times 5 is minus 15. Minus 15 plus 10 is negative 5. But you have 5. So 5 plus negative 15 plus 10 is 0, right? Same thing here. 2 times negative 3, negative 6. Negative 3 times negative 6, negative 18. And minus 12. Oh, that's positive 18. 18 minus 12 is 6. 6 minus 6 is 0. Right? So you do get 0 if you compute everything. So we know that it's a solution. So that will be basically the approach that we are going to take. Okay? And then later on, I'll try to explain how we can exploit this property to really find the general method for solving this type of equation.